Hi, I am Shahnawaz. Uh, in this lecture, we will discuss terminals and initials. But let us recall what we did in last lecture. So, suppose we have a category A, and suppose A and B are two objects in the category A. Then the product of AB is an object denoted by A times B. So, this object is equipped with two maps called the projections. So we have a projection P from A cross B to A and a projection Q from A cross B to B. So then this object A cross B is said to be the product of A and B if for all morphisms F from C to A and all morphisms from I mean and G from C to B, there is a unique morphism, say F comma G, or sometimes we denote this by F cross G. So this is a morphism from the object C to A cross B, such that this diagram commutes. So we have C here, we have A cross B here. From A cross B to A, we had a projection P. From A cross B to B, we had the projection Q, and we have a morphism F from C to A and a morphism G from C to B. So if that is the case, then A cross B is said to be the product of A and B if this is this unique morphism. So this is a unique morphism, and this morphism is given by F comma G. So we say that uh, if this diagram commutes, then A cross B is the product of A and B. That is P composed with Fg is F and Q composed with Fg is G. Now let us define what do we mean by uh, the binary products. A category with binary product. So we have this definition. So let A be a category if for all object say A and B in category A, there exists there exists a product there is a product A cross B, then we say A has all binary products. So we say A has all binary products. Now we have a proposition. Let us suppose A is a category with all binary products. So let A be a category with binary products. With binary products. Then given given morphisms, say F from the object A to C and a morphism G from object say B to D. There is a unique morphism let us call that F cross G. So this is a morphism from object A cross B to object C cross D, such that uh, P1 composed with the map F cross G is F composite P, and Q1 composite F cross G is G composite Q. Now, what are these P1 and Q1? And I mean PQ and P1 PQ. Sorry, Q1. So they are the projections where uh, P1 while PQ are projections on A cross B to A and B respectively, and P1 Q1 are projections of A cross B to C and D respectively. Let us prove this. So note that one can see that the morphism. So note that if we look at the morphism F composite P, so one can see P is a projection from A cross B to A. So this is the projection map, and from A to C we have the map F. So F composite P is a morphism from the object A cross B to C, and similarly G composite Q is a morphism from uh, the object A cross B to D. So then C cross D being the product of C and D, so then C cross D being a product, being the product of C and D, uh, then there is a unique morphism. So then there is a unique morphism F cross G, I mean F cross G from A cross B to C cross D, such that the diagram commutes. Now here we consider the product of C and D. From C to D to C we have the projection map P1, and from the same object to D we have the projection map Q1. Now we consider C cross D to be the product of C and D, and we use the definition of product. So for any object, let us suppose in particular, I mean the object A cross B. So since we are given a map from A cross B to C, which is a map F composite P. So first we have P, which is a projection map from A cross B to A, and from A to C we had a projection map F. Similarly, from A cross B uh, to A to B we have the projection map uh, Q. and from B to D we have the projection map. Uh, from B to D we have the morphism G. So if we look at this map, this is the map F composed with P. Similarly, from A cross B to D, we have the projection. We have the map G composite uh, Q. Now, using the definition of product of C and B, there is a unique map, and we call that map F cross G, such that this diagram commutes, such that the diagram commutes. That means uh, that is, if we first go via the map F cross G followed by P1, we get this map F composite P. And similarly, if we first go via the map F cross G followed by Q1, we get this map, which is the map G composite Q. So this proves the result. So actually this result is immediate from the definition of product of two objects. Now we have the definition of a terminal. So let us suppose we have a category A. So a terminal object. So this is actually an object in a category. So a terminal object in a category A is an element T of the object class of A, such that for all objects in A there exists a unique morphism, say K, from X to T. So such an object is called a terminal. For example, if we consider the category set, so let us do some example. So consider the category set. So in set, every one element set is a terminal. So one element set is a terminal, because for any object, so if we look at an object, so because for any object, say X in this category, and if we take a singleton set, say A in the same category, then there exists a unique morphism, say K from X to A, given as, so it maps every element of object X to A, such that K takes this little x to A for all X in X. Now we want to prove that these terminals in a category are unique up to isomorphism. So we have a proposition. say if T and T prime are terminals in a category say A, then there exists a unique morphism say F from the terminal T to T prime. I mean the terminals are unique up to isomorphism. That is terminals in a category terminal in a category is unique up to isomorphism. That is prove this. So suppose we have two terminals T and T prime. So let us first suppose that T prime is a terminal. Suppose T prime is terminal in a category A. In a category A, then by definition, the for any object X in category A, there is a unique morphism from X to A. So in particular, there is a unique morphism from the object of T to T prime. So then by definition, there is a unique morphism, say F from T to T prime. So one should note here we are assuming that T prime is a terminal. So then for any object in the category, there is a unique morphism from that object to T prime. In particular, there is a unique morphism F, say F from the object T to T prime. Here we are considering T just an object. So we are not taking T as a terminal. So we are just taking T as an object. And this T prime being terminal, there is a unique morphism from T to T prime. Similarly, let us consider T a terminal and T prime an object. So then we can also have a unique morphism from T prime to T. So similarly, T being also a terminal in A, and there exists a unique morphism, say G or say F prime from T prime to T. Now we have morphisms. Now consider the morphism. So now F prime composed with F. So this is actually a morphism from T to T because from T to T prime we have a morphism F, and from T prime to T we have the morphism F prime. So from T to T we have the morphism F prime to F prime. Let us consider this. So now consider this morphism from T to T. So note that T being a terminal, so there is also the identity morphism from T to T. So since T is a terminal, there exists a unique morphism from any object to T. In particular, there's a unique morphism from T to T. There's a unique morphism from T to T. T. Since uh, I mean we know T on object T, we always have the identity morphism. So here we can assume that the unique morphism from T to T is the identity morphism. So since T is the terminal, there is a unique morphism from T to T, that is the identity identity morphism, which is given by 1 sub T. But here we also claim that f prime composite f is also a morphism from this object T to T. So that means these two morphisms, I mean f prime composite f and 1 sub T, they are equal. So by uniqueness, the morphism f composite f is same as the identity morphism on T. Similarly, we can prove that we can show that f composite f prime is the identity morphism on T prime. So that means this f is actually an isomorphism. So hence f is an isomorphism. So is f prime. Now f is a morphism between T and T prime. Now since f is isomorphism, that means I mean these operators T and T prime are isomorphic. So hence terminals are isomorphic. So they are isomorphism. So hence T and T prime are isomorphic. Now let us define what do we mean by exponential. So, but before that, we know using the dual notion for this terminal object, we have, I mean, the dual notion of this terminal object is an initial object. So we can have the definition of an initial object. So the dual of a terminal in a category is called an initial object. That is, if A is a category, then an object I is called the initial object if for any object say y in A, there is a unique morphism Let us call that morphism, say G from object I to Y. So note that for terminal we have the morphism F from X to T. So one can note over here, if we replace T by I, this arrow gets reversed. So that is what we mean by dual. So in dual we always reverse arrows. So like terminals, these initials are also unique after isomorphism. So we have this proposition in a category A. So in a category, the initial objects are isomorphic. So the proof is similar, using a dual notion in this proof over here. So if we use the dual notion in this proof, I mean, if we just reverse the arrows and we replace t and t prime by I and I prime, we get the desired result. So the proof follows using dual notion in the proof of terminals. Now we just want to define the exponential, which is also sometimes called as a function space. So we have this definition. Suppose fancy A is a category with binary products. So with binary products. So given say objects B and C, a function space or exponential. So a function space or exponential is an object. So this is actually an object denoted by B to the C. So any pair of objects, uh, I mean, if we have two objects B and C in a category A, then we have the exponential B to the C. So this is C to the B. Let us call this C to the B. And this exponential is uh, equipped with, so this is equipped with the evaluation morphism, with the evaluation morphism. That is, we have a map, say epsilon, from the exponential c to the b times b to c, such that for all morphisms, say f from a cross b to c, there is a unique morphism f bar from a to the exponential, such that the diagram commutes, such that the following diagram commutes. Now the diagram is like this. So we have the object A cross B, and we have a map F from A cross B to C. And here we have this object, I mean the exponential times B. So from this object to C, we have the evaluation map epsilon. So if we are given these, I mean these conditions, then there exists this unique morphism f bar from this object A to object to C to B. But here we have this object B as well. So for that, we can write here the identity on B. So such that this diagram commutes. Now to understand this, let us do some examples. Let us consider the category of sets. So we have an example. So in the category set for any two objects, say B and C, in this category, the exponential C to the B are actually all morphisms or set functions from the set B to C. So this is sometimes denoted by B comma C with square brackets. Now here the evaluation map is, so we can embed, I mean we can have an evaluation map on this exponential, which is given as, so there is an evaluation map, say epsilon from the exponential C to the B cross B to C, and this evaluation map takes an element in this exponential, which is some map, let us call this G, and it takes an element inside B, let us call this B, and it maps this element to the element G evaluated at B. So since G is a map from B to C, then G evaluated at B is an element of C. So this makes sense. So now we have this map. So here we have A cross B, and we have C here. So from this object C to the B cross B to C, we got our evaluation map. Now we have defined this map over here, I mean from the object A cross B to C. So given a map F from A cross B to C, so now to define this map, what we do, so we fix some element A in A to get, so F sub A from B to C is the map which is given as, which take is the element B to the element F of AB. So I mean we can define this map like this. So F of AB goes to F sub A of B. So this is the map F. So it takes an element AB to F sub A of B. Now we have to define this map. I mean, we have to prove there is this unique map the evaluation map. We have to first exhibit a map F bar from A to C to the B. I mean, a map from A to the exponential CB. So, so that we have a function F bar from A to C to the B. So this F bar is such that it takes an element A and maps to an element C to the B, which is a map from B to C. So we know here this F sub A, this is actually a map from B to C, because F A of B is an element inside C. So somehow we define this, we define this map F bar such that it takes an element A inside this object A and it maps it to the element F sub A. Now, if this is the case, we get such that, so from A to C to the B, from this A to C to the B, we have the map F bar. From B to B, we have the map identity on B. So this is the map from A cross B to C to the B cross B. Such that now we have to prove that this diagram commutes. Such that, so if I look at this composite map, the map epsilon composite with F bar cross 1 sub B of some element in AB. So this is equal to epsilon of F bar cross 1 sub B of element AB. So this is same as this epsilon of, now this gives us F bar of A comma B, because identity on B is B. So let us write this as 1 sub B of B. So this is same as epsilon of, now F bar A. F bar A is mapped up to F A. So this is F sub A of B. Now epsilon of G comma B is the map G evaluated at B. So this gives us the map F sub A evaluated at B. But F sub A evaluated at B is same as F of AB, because we have this map here. So AB goes to F sub of AB. The map F sends the element AB to F sub AB. So that is the diagram commutes, i.e. epsilon composite with F bar 1 sub B is same as F. So this gives, this is an example of an exponential in the category set. So as we we use the dual notion in terms of terminals, so we can also use the definition of the dual notion in case of the products. So using the dual notion of a product, we get the co-product of two categories, two co-product of two objects. So we have one more definition here. So let A be a category and suppose A and B are two objects there. So let A be a category and A and B are two objects in the category A. So then the then the co-product of AB, then the co-product of A and B denoted by A co-product with B. So this is the co-product equivalent with co-projections. So in products we have the projections, and here we have the co-projections. So the the co-product is an object. Let us erase this. So the co-product of A and B is an object. A cup B equipped with the co-projections. To note that this came back from a search. So we have to reverse the arrows. So we have an arrow from the object A to A cup B, and an arrow from object B to A cup B. And let us call this P, let us call this Q, such that for any morphism, say F, from now we have taken morphism from A to A cup B. So from A to A cup B, and a morphism G from B to A cup B. There is a unique morphism. Now this morphism, sorry, this is not A cup B, this is some object C here. And G from, use an arrow from object B to C. So for these morphisms, there exists a unique morphism. Let us call that H from the co-product of A and B to object C, such that the diagram, now the diagram here is like this. So we have C here, and we have the object A cup B. So from A cup B to C we have this morphism H here, and from A to B we have projections. So it's the projection P, it's the projection Q, and the morphisms F and G. So it is such that this diagram commutes, such that this diagram commutes. So like products, we have a result here. I mean, the co-product of two objects is unique up to isomorphism. So the proof is similar, only we have reversed the arrows in the proof of products. So the co-product of two objects in a category is unique up to isomorphism. So the proof is similar, only one need to reverse the arrows. So the proof follows by using dual notion. Uh, the proof of products.